Bismillahirrahmanirrahim. We have two orthogonal projection matrices, P1 and P2 of size n by n. Both matrices are Hermitian. Both are idempotent. P1 Hermitian is equal to P1 squared is equal to P1. P2 Hermitian is equal to P2 squared is equal to P2. The rank of P1 is R1. P1 has R1 unity eigenvalues and n minus R1 zero eigenvalues. The rank of P2 is R2. The sum of the two ranks is less than or equal to n. There is a third matrix, omega, of the same size, n by n. P1 plus P2 plus omega is equal to the identity matrix. For circularly symmetric Gaussian random vector x, whose mean is the O0 vector and whose covariance matrix is identity, we are interested in obtaining the probability density function of the quadratic form x Hermitian omega x. We also need to show that the quadratic form x Hermitian omega x is independent of these two quadratic forms involving the other two matrices P1 and P2. Consider random vector x in the column space or the range of P1, then P1x is equal to x. If the orthogonal projection matrix is applied to a vector in its range, we get the vector back. To prove this real quick, note that if x is in the range of P1, then there exists a vector y such that P1 times y is equal to x. Multiply both sides from the left by P1, we get that P1 squared y is equal to P1x. P1 squared is equal to P1 because P1 is idempotent. P1y is equal to x. Vector x is equal to identity times itself. Write down identity in terms of the three matrices in our problem. So x is equal to P1 plus P2 plus omega times x. P1 times x, that's x, because x is in the range of P1. We also have P2 plus omega times x. We have P2 plus omega. X is equal to the O0 vector. Multiply both sides from the left by x Hermitian. We get x Hermitian, P2x plus x Hermitian, omega x equal to 0. Note that this quadratic form is equal to x Hermitian, P2, P2x. Because P2 is idempotent, we can also add Hermitian here. It's an orthogonal projection matrix, so it is both idempotent and Hermitian. This quadratic form is P2x all Hermitian times P2x. That's the L2 norm squared of vector P2x. This is non-negative. It is given in the problem statement that omega is a positive semidefinite matrix. So x Hermitian omega x is also non-negative. We have two non-negative quantities. Their sum is exactly equal to 0. Then both must be equal to 0. This L2 norm squared is equal to 0. So the vector is equal to the O0 vector. P2 times x is the O0 vector in the n-dimensional space. What is our conclusion? We have started with a vector living in the range of projection matrix P1. This same vector must be in the null space of P2. All vectors in the range of P1 are in the null space of matrix P2. This implies that P2, P1 is equal to the O0 matrix. The first column in this matrix is P2 times the first column in P1, which is in the range of P1. The second column in P2, P1 is P2 times the second column in P1, which is a vector in the range of P1, and so forth. P2 times P1 is the O0 matrix. Take the Hermitian of both sides. We get that P1 Hermitian, P2 Hermitian is the O0 matrix. P1 Hermitian is equal to P1, P2 Hermitian is equal to P2. Also, P1, P2 is the O0 matrix. Let's investigate the matrix P1 plus P2, which is relevant to our problem. This sum here plus the positive semi-definite matrix omega is identity. The claim is that this matrix is an orthogonal projection matrix. This matrix is Hermitian. What if we multiply it by itself? We get P1 plus P2 times P1 plus P2. We have four terms. This is the O0 matrix. This is also the O0 matrix. This is P1, this is P2. P1 plus P2 is Hermitian. P1 plus P2 is idempotent. It is an orthogonal projection matrix. Note that the intersection of the range of P1 and the range of P2 is just the O0 vector. If x is in the range of P1 and x is in the range of P2, then x is equal to P1x. But also x is equal to P2x. This is the O0 matrix. This is the O0 vector. The only vector living in both column spaces is the O0 vector. Here are our results so far. We had three matrices, P1, P2, and omega. Their sum is identity. P1 is an orthogonal projection matrix. P2 is an orthogonal projection matrix. Omega is a Hermitian positive semi-definite matrix. We have proved that P1, P2 is equal to P2, P1 equal to the O0 matrix. P1 plus P2 is an orthogonal projector. The intersection between the range of P1 and the range of P2 is the O0 vector. Let's go back to this expression. Multiply both sides from the left by the orthogonal projection matrix P1. We get P1 squared, which is P1. P1 times P2, that's the O0 matrix. We also get P1 times omega, and this is equal to P1. P1 omega is the O0 matrix. Take the Hermitian of both sides. Omega Hermitian is omega. Omega is a Hermitian matrix. P1 Hermitian is P1. This product is also the O0 matrix. We can repeat the same step, but we multiply from the left with P2. We also conclude that P2 omega is the O0 matrix, and omega P2 is the O0 matrix. What is the rank of the projection matrix P1 plus P2? This is equal to the rank of P1 times P1 plus P2 times P2, which is equal to the rank of P1 Hermitian plus P2 Hermitian. This matrix here can be written as a matrix of size n by 2n. In that fat matrix, we place the n columns of P1 followed by the n columns of P2. To get P1 Hermitian plus P2 Hermitian, we multiply this matrix by its Hermitian. We have here a 2n by n matrix with blocks B1 Hermitian and B2 Hermitian. If we have a matrix A, then the rank of A is equal to the rank of A Hermitian, equal to the rank of A Hermitian, equal to the rank of A Hermitian A. But this equality is what is relevant to us now. The rank of the matrix times its Hermitian is equal to the rank of the matrix. The intersection of the span of the columns here and the span of the columns there is the O0 vector. Because the intersection of the column spaces is just the O0 vector, this rank is the rank of P1 plus the rank of P2. R1 plus R2. Omega is equal to identity minus P1 plus P2. P1 plus P2 has R1 plus R2 unity eigenvalues, n minus R1 plus R2 zero eigenvalues. This means that omega has R1 plus R2 zero eigenvalues and n minus between brackets R1 plus R2 unity eigenvalues. The rank of omega is n minus R1 plus R2. Now let's do the probability part of the problem. We have vector x. X is a circularly symmetric Gaussian random vector. The mean of x is the O0 vector. The covariance matrix is identity. Consider an orthogonal projection matrix M. The PDF of x Hermitian Mx is the PDF of 1/2 a chi-squared random variable with a number of degrees of freedom equal to 2 times the rank of n. Let's review this result. Here is the eigendecomposition of M. The diagonal matrix with the eigenvalues. It has a number of ones equal to the rank of M. Say that the rank of M is equal to R. So we have R eigenvalues equal to 1. The remaining n minus R eigenvalues are equal to 0. Rewrite this quadratic form, keeping the columns in matrix Q that are associated with the unity eigenvalues. So we have here x Hermitian, Q tilde, the R leftmost columns in Q, times Q tilde Hermitian times x. X is of size n by 1. Q tilde is of size n by R, where R is the rank of the orthogonal projection matrix M. The quadratic form is equal to the L2 norm squared of the vector Q tilde Hermitian x. This is an R-dimensional vector. Let's call it Z. Z is an affine transformation of x. X is a Gaussian random vector, so Z is a Gaussian random vector. X is circularly symmetric, so Z is also circularly symmetric. To fully characterize the distribution of Z, we need the mean, which is Q tilde Hermitian, times the expectation of random vector x. This is the O0 vector, because the components of x are zero mean. The covariance matrix of Z is the expectation of Q tilde Hermitian x Hermitian Q tilde. This is Q tilde Hermitian. The expectation of x Hermitian is identity. Then we have Q tilde. This is Q tilde Hermitian Q tilde. Note that the columns of Q tilde are taken from matrix Q, and matrix Q is unitary. It came from the eigendecomposition of a Hermitian matrix. Q tilde Hermitian Q tilde is equal to identity of size R by R. The components of vector Z are IID, Cn, 0, 1 random values. The quadratic form is the L2 norm squared of vector Z. The quadratic form is equal to the real part of Z1 squared plus the imaginary part of Z1 squared plus the real part of Z2 squared plus the imaginary part of Z2 squared, all the way to the real part of ZR squared plus the imaginary part of ZR squared. Multiply and divide by 2. We have 1/2 square root 2 times the real part of Z1 squared plus the square root of the imaginary part of Z1 squared plus the square root 2 of the real part of Z2 squared, and so forth. Our random variables have the property that the real and imaginary parts are independent. Moreover, the variance of each is 1/2. A random variable with variance 1/2 multiplied by the square root of 2 has a variance of 1. What do we have here? we have the sum of the squares of 2r real-valued standard Gaussian random variables. This sum is the chi-squared random variable with 2r degrees of freedom. The quadratic form is equal to the chi-squared random variable multiplied by 1/2. Given this piece of information, x Hermitian P1x has the PDF of 1/2 a chi-squared random variable with 2r1 degrees of freedom. X Hermitian P2x has the PDF of 1/2 chi-squared random variable with 2r2 degrees of freedom. Finally, x Hermitian omega x has the PDF of 1/2 a chi-squared random variable with 2 times n minus r1 minus r2 degrees of freedom. The last part in the problem is to show that these quadratic forms are independent. Note that this quadratic form is the L2 norm squared of P1x. This quadratic form is the L2 norm squared of P2x. That quadratic form is the L2 norm squared of omega x. These are Gaussian vectors. We have proved that if we pick two distinct matrices from this collection of 3 matrices, we get a product that is equal to the O0 matrix. P1, P2 is O0, P2, P1 is O0, P1, omega is O0, and so on. Let's take this Gaussian vector and that one, both are zero mean. Let's compute the cross covariance, the expectation of B1x times omega x Hermitian. This is the expectation of P1x x Hermitian, omega Hermitian, which is equal to omega. This is P1, the expectation of x Hermitian times omega. This is identity, so we get P1 omega, and this is the O0 matrix. These two Gaussian random vectors are uncorrelated. Their cross correlation matrix is the O0 matrix. Note that the random variables here and there are jointly Gaussian. If we stack matrix P1 on top of matrix omega and multiply by x, the top n random variables are P1x, the bottom n random variables are omega x. X is a Gaussian vector. It is a vector with IID components. IID Gaussian random variables are jointly Gaussian. The random variables here and there are an affine transformation of jointly Gaussian random variables. Thus, those random variables are jointly Gaussian. Now we have proved that they are uncorrelated. And for jointly Gaussian random variables, uncorrelatedness implies independence. We can repeat this exercise using P2x and omega x. We can do it a third time using P1x and P2x. In all cases, we get that these Gaussian random vectors are independent. So any functions of them are independent of each other. These 3 quadratic forms are independent.